Welcome back, everybody. And the topic today is to wrap up some of these examples about the particle hole formalism. And then we are going to use that as an entry point for our first real many-body method, which is full configuration interaction theory, or what is often called in nuclear physics for the shell model. And in atomic physics, it was also called the shell model. But then people changed the name to full configuration interaction theory. And that's often how you will see it in a general many-body textbook. Now, the thing I want to do first is actually to repeat some of the things which we did yesterday. And if we now look at the particle hole formalism, what we did when we had a new reference vacuum was that we were able to redefine the Hamiltonian. So we have defined the vacuum in terms of for fermionic system, a Slater determinant. And this Slater determinant is then something which we earlier defined as a product of all these single particle states up to the number of full single particle states, which we also would label sloppily as a Fermi level. So this is essentially, in second quantization, this definition of the Slater determinant. And then we had this new commutation rules and contractions. So we had that this contraction is different from 0 if P and Q are states above the Fermi level. And then we have an AP dagger, AQ, which is equal delta PQ in case P and Q are below the Fermi level. So F indicates all these single particle states which are being filled up. Now, what we could do then is to rewrite the Hamiltonian still with using a normal order chain of operators, but now introducing the vacuum. So that changes slightly the definition of the Hamiltonian. And we rewrote the Hamiltonian in terms of one term, which is a one-body operator. And then we have the two-body. And clearly, if you're doing nuclear physics, we can also have three-body interactions, etc., etc. And then we have a reference energy. So let's just remind ourselves quickly about these quantities. And this reference energy is the expectation value of this new vacuum state or reference state, as we've been calling it. And this is presumably something which we can calculate. Whether it's easy or not depends on the type of basis you have and also the type of interactions you have. So if you're dealing with atomic physics and you have hydrogen type of orbitals, often the two-body integrals are equations which you can, or integrals which you can solve analytically sometimes for some specific single particle states. If you're doing nuclear physics, one uses often the harmonic oscillator, and the harmonic oscillator has, for the nuclear force, has equations which you need to solve numerically. If you're dealing with the Coulomb interaction and have harmonic oscillator basis states, you can actually find analytical expressions for that. So some of these basis states allow you to calculate some of these integrals in a pretty straightforward way, whereas in other cases, the evaluation of these integrals can be pretty laborious. Now, one of the things which we also did was to define new states. So we had this chain of possibilities. So what we are doing is actually to reorder the set of Slater determinants which we have in terms of particle hole excitations. Now we are looking at just a system with n particles. So we are not changing the number of particles of the system. So if you're looking at a reaction where you remove an electron or you remove a proton or a neutron, then you have to take the overlap between a system with n particles and a system with n+1 or n-1 particles. So this state here is something which we would label as a phi IA. and this is given by AI, A, and AI. I always mess up the pronunciation of I and A. And then we had a two-particle, two-hole state, which we would label as an IJAB. And this would be given now by 4 operators, 2 creation operators and 2 annihilation operators. And then we can proceed very much like that, which means that when I'm going to introduce a new notation now. So I will define a general state with an uppercase H and an uppercase P now, where P now stands for N times, so this is an uppercase number of particle states. And this uppercase H stands for N whole states. So this is now just a generic labeling, which indicates a particle hole excitation. N, this number N, could obviously be 0. So it can be 0, 1, 2, and this runs up to the number of particles which we have. Because if you say we have 4 particles, just as an example, and we have 8 single particle states, but this could be doubly degenerate. So suppose that these are doubly degenerate states. We have a Fermi level here, and then we can place a particle with spin up, one with spin down, one with spin up, and one with spin down. So this would be something which we now, if we let this be the Fermi level, this would be a 0 particle, 0 hole state. And this is the one which we label as a phi 0. So that is our ansatz for the ground state of the system. So whether that's a good ansatz or not depends on the type of interactions we have, the type of single particle basis, etc., etc. Now, you can then promote these guys, all of them, above the Fermi level. So you could have these 2 up here and that one up there. So the red one would be what we call a 4-particle, 4-hole excitation. So this is just a way by which we now are going to reorder all the Slater determinants which we can make. So let me just give you an example here. And since we have people doing nuclear physics, let's take an example from nuclear physics. So we have a nucleus like oxygen-16. And in nuclear physics, it's pretty common to assume a harmonic oscillator as a single particle basis. This works as a pretty good approximation for the low-lying states. So this is a basis, and you can see that because you can fit a single particle basis. There's something which is called a Wood-Saxon potential in nuclear physics. And you can get an effective potential then when you fit to experimental data and you extract single particle properties. Remember that a single particle observables in a many-body system is not an observable. So single particle states are not observable. But you can extract an effective potential which traps the motion of protons and neutrons by fitting the solution of the Schrödinger equation to experimental data. So this is fully possible, and people have actually fitted these potentials, and this potential which you see here, so this is an effective potential as a function of R, and it can vary from nucleus to nucleus. It has a very simple form, and it's easy to solve the one-body Schrödinger equation for that type of potentials. And this potential has some discrete bound states, and then obviously there is a continuum of states above that. Now, if you then think of the harmonic oscillator, if you just take this part, looks something like this. So it's often a pretty good approximation if you tune the parameters to reduce something which looks like this effective potential, which is called a Wood-Saxon potential. So in nuclear physics then, what you would have in oxygen-16, you have 8 protons and 8 neutrons, which means that you could now make a model of the system using the harmonic oscillator in 3 dimensions. So the harmonic oscillator in 3 dimensions, when you now switch to spherical coordinates, it has quantum numbers which look like those which you have in atomic physics, like S waves, P waves, D waves, etc. And these states then form a specific structure where you now can have a state, a 0 S state. This is a single particle state of the harmonic oscillator. And if we now put protons here, we can have 2 protons here in this state. And then we have the next shell, which is called 0p. Sorry, 0p here. And here we can have 6 protons, which we can fill in. And these form what are called magic numbers. And in nuclear physics, magic numbers are relevant ways of identifying specific properties of nuclear, because it requires energies to break a pair of neutrons or protons and produce an excited state. So actually, the first excited state in oxygen-16 is a state with total angular momentum 0. And it has an excitation energy of 6 mega electron volts, which is a pretty high excitation energy compared with electronic physics or atomic physics or condensed matter physics. But this gap is actually pretty large, and is a typical evidence of a closed shell structure. So this kind of picture functions very much like a good ansatz for the system. So we would have now, for neutrons here, you would then have 6 neutrons, which you can fill in into this state. Now, if you're thinking of the harmonic oscillator, this, if you do that in Cartesian coordinates, then you would have nx equal ny equal nz as quantum numbers equal to 0. Then when you go to the next level in the harmonic oscillator, you would have 1 with nx equal to 1. There's a new state here, so these are degenerate in energy. And then we have 1 with nc equal to 1, and the other ones are 0. And then you see you can have, in Cartesian coordinates, you can then place 2 particles here, 2 here, in each state here, due to the spin degeneracy. So this is just equivalent quantum numbers, where you've gone from a Cartesian representation to a spherical representation, which often simplifies your machinery when you're calculating specific expectation values or integrals of, let's say, the interaction. Now you can continue now, and you can have states above the Fermi level. And now I'm just setting up the quantum numbers here of what's called the SD shell. So this mimics very much, for those of you who are not familiar with the harmonic oscillator in 3 dimensions, this mimics very much what you have for the hydrogen type problems, where you have S waves, P waves, D waves, F waves, etc. And here you can place 12 particles, and then you can move up here, and you have something which is called the 1p0f shell. And the degenerates here so that you can put in 20 particles. Now, the harmonic oscillator has an infinity of single particle states. And that means that this basis here just moves on to infinity. But suppose now that we are making an effective Hilbert space where we stop here, like that. And now we want to scatter 8 protons in 40 single particle states. And we can do the same with the neutrons, so we can scatter 8 neutrons in 40 single particle states. So if we now look at the number of realizations which we can do with neutrons or protons, so number of proton configurations, in that case, this is equal to the combinatorial factor of 40 and 8. So we have 40 single particle slots. And when we do the math here, this should give us 32 factorial, 8 factorial, and this is roughly 10 to the 9. So that's, even for this small space, this is a huge number of determinants. Now, what we often end up doing, so if you look at a drawing here, in terms of single particle basis, you can now think of your full Hilbert space. This is your full Hilbert space. This includes all possible realizations. So in principle, this is infinite. So this is your full Hilbert space. Now your actual Hilbert space, so the full Hilbert space will also contain bosonic degrees of freedom. So your actual Hilbert space could be something like this. So this could be the actual space. And in this case, when we're dealing with fermions, we have reduced the dimensionality because we are taking into account some specific symmetries. So fermions have to be antisymmetric. The total wave function has to be antisymmetric, which means that if you look at all possible realizations, the actual space, when we have picked some specific symmetries, is then smaller than the full Hilbert space. Then at the end, we are ending up here, which is our effective Hilbert space. So I'm drawing this in 2 dimensions now, but in principle, this is a multi-dimensional space. So you could think of this as a particle A and a particle B, and all the realizations you can make between 2 particles. And this is your effective space. So all of many-body physics deals with running calculations in such an effective space. So you see that even such a system here, where we have made an effective Hilbert space, which only contains 40 single particle states, this is a huge dimensionality. The total number of Slater determinants for this system is equal to the number of proton determinants times the number of neutron determinants, which means that the total dimensionality for this problem is 10 to the 18. And you don't want to diagonalize a matrix of dimensionality 10 to the 18th, even in this space, which we would call a baby space when it comes to the amount of degrees of freedom. But in many occasions, if you have a proper way of dealing with an effective Hamiltonian, this can still give meaningful results, which are not that far from experiment. Yeah?
You can constrain the dimensionality.
Yes.
Because
you don't need all of them. Yeah. So you could say that now I'm only interested in states with a specific symmetry. So we've already done 1 reduction of the full Hilbert space because we are not taking into account solutions where the wave function is symmetric. And that obviously reduces the dimensionality. And then we could say that we are only interested in states with a specific spin. And that will also reduce the dimensionality of the system. And clearly, a space which is infinite is something we cannot deal with, obviously. And we always end up with dealing with some kind of effective Hilbert space. So the question is then, how consistent are we in the derivation of the effective Hamiltonians for this effective Hilbert space? So if we now go back a little bit to where we were yesterday, so this was a kind of repetition, when we have this kind of way of ordering the states now in terms of particle hole excitations. So we are going to rewrite a wave function for the full Hamiltonian, which now is composed of 1, the ansatz for the ground state, obviously, which will be this one. But then we are going to look at the excitations above the Fermi level. So the Fermi level here in oxygen 16 will then be defined by us filling up all single particle states up to the p state, the 0p state. So that is an ansatz for the ground state of the system. So what you see here is actually our phi 0. And then all the other states are now going to be relabeled in terms of such excitations. So this is just a way to reorganize your Hilbert space, okay? So one of the things which we did yesterday, just to remind you of that, was then to calculate some specific expectation values of, let's say, or transitions or overlaps between the ground state and some selected states here. So this would be a one particle, one whole state. And when we looked at the Hamiltonian, we had rewritten that one in terms of these two terms plus the reference energy. Let me quickly remind you of these quantities. So Fn is simply given by the one body operators with an integral over P with an operator F and Q here. And then we have these normal ordered states on the operators with respect to the new vacuum. And where this integral is now given by the non-interacting piece of the Hamiltonian, plus a correction due to states below the Fermi level. So Pi of V of Q of I. And these are anti-symmetrized matrix elements. And V of N was just a two-body operator. We have a matrix element, PQ, V, RS, anti-symmetrized, and this is multiplied with this normal ordered chain of operators. So one of the things which we did then was when we calculated these expectation values, what we found for that specific case here, so for this, let me just go back here and set up the expression as we derived them yesterday. So this quantity which we found yesterday is given by, so this quantity here, P of I, A, was now given by the integral over I of F and A. And what we also found yesterday is that V of N of IA was given by 0. So it means that that specific integral which we have here with the Hamiltonian of phi I of A was simply given by this integral defined by the operator F. Then we also calculated the expectation value of phi of H, and then we took phi ij of AB, and we found that this one was equal to the anti-symmetrized matrix element between the two whole states ij and the two particle states AB. So this is an example of elements which we can calculate with Wick's theorem pretty easily. Now, what we also did was to introduce a diagrammatic notation. So that this quantity which we have here, when we now look at the diagrammatic notation, then we introduced for particle states, we would have an arrow which points up, and for whole states, we have an arrow which points down. Now, this term, the first term which we looked at yesterday in a diagrammatic representation was this term here. So let me just quickly repeat some of these results which we had yesterday. So this specific term, F of A, is given by these integrals which we have here, plus the sum over J, and these are states below the Fermi level. So when you see letters like I, J, K, these are states below the Fermi level, and I will normally skip this sign here, but I'm putting it in here, but in general, I will just skip it because it's uniquely defined that the states I, J, K, L, etc. are states below the Fermi level. And this is given by This is I of J, of V, of A, J, and this is an anti-symmetrized matrix element. Now, this term here in a diagrammatic representation, and when we now introduce whole states, so we have the operator for the non-interacting part of the one-body part of the Hamiltonian. We have an incoming state A, but then the whole state, as we said yesterday, is now a state which points downwards. So if we were not to introduce this new vacuum, we could think of this as a state which points up, but then we are bending it down, which means that we end up having it written like this. So this state which we have here is just bent down, and we would write that contribution like that. Now, then what we have diagrammatically is this sum over J, and then we have two terms. So one term where I now have the particle state A coming in here, and then I have a whole state J, which is actually coming in, and then I have a whole state J, which is leaving, and then I have a whole state I, which is also leaving, and it's pointing downwards. So we are putting labels here, so this will be A, and this is I, this is J, and this is J. So if you think of this in the particle formalism, which we started with, this will be an I, this will be an A, and then I would have a J pointing up and a J pointing up, if we use the true vacuum as reference state. But we are going to use this particle whole formalism for the rest of the semester. Then the next term is now given by this diagram, which we wrote like this. So we have the state J, and then we have the state A, which comes in here. And then we have the state I, which then, I have, what did I do now? Yeah, this is the exchange term. So the state I is a state now which leaves. So if we write it out, it would look something like this. So I have a state I and a state J, and then I have interchanged these two guys. So I have a whole state, this state A here, that's the exchange term, and I have a state I like this. So this will be given now by a state I here, and then I have a state A coming in like that. So these diagrams are normally rewritten in terms of a summation over whole states. Actually, we should be a little bit more careful here, because what I did here was to anticipate. Let me just rewrite this one. So I have a state I, which is outgoing, and then I have a state J, which is incoming. So I would have I and J, and so that means that I should have a J here, but I would also have a state J, which comes in here. Now, if you now look at this term which we have here, it's common to take away the summation and replace that one with what we call a closed loop or a loop. And it's common to rewrite this one in this term in this way here. So I have an I and an A and an I. And then I have plus, and this diagram is going to look like this now. So I will have an I here. I have an A, and then we are bringing this line J like that. So this diagram has one closed loop. And one internal whole line. And each internal whole line gives rise to a factor of -1. Each closed loop gives rise to a factor of -1. So this in total gives a factor of +1. And then I can then read off the integrals directly from the indices for the particle states and the whole states. So by then using the rules for reading off the specific way the integral is set up, this is simply given by A and, no, sorry, i.e. I of J, of V, of A, and J. So this is the way I now read off when I want the analytical expression for all the expression listed in a table for that specific integral. Okay? So this is the way I would then represent this operator which we have here, this transition probability or overlap matrix elements, whatever we are actually calculating. And if we now move to the phi 0 to the operator from the state ij and ab, then this was given simply by ij of v of ab. So if I'm writing this now in terms of diagrams, what I'm going to have is actually something, actually yeah. So this will be when I write it diagrammatically, if I were to use the particle formalism, this is given by ij, and then I have a state AB coming in. And now I can bend this in terms of the particle Hall formalism. So this will be given by this term here. So I would have an A and an I, and then I would have a B and a J here. Actually, I think I inverted when I did the, I think I was a little bit too much in a hurry here. I think I have actually inverted the, let me just check it again here. No, it should be that. So this is what we would call a two-particle, two-hole excitation or de-excitation. So this is a two-particle, two-hole state which we're creating. Now, if we then are looking at the more complicated terms, we are just coming back to that a little bit later. So let's now move on a little bit. I'm going to give you a small exercise. And that is to calculate the expectation value of this term here, where I is different from J and A is different from B, just as a small exercise. So that means that what you need to set up is actually this quantity here, phi 0, and then you will have an AI and AA, and then you have the Hamiltonian, and then you have an AB dagger of AJ acting on phi 0. And then you need to look at the terms here where you have E0 ref plus this f of n, which is then proportional to an operator AP, AQ, and then plus V of n, which is then proportional to an AP, AQ, AS, AR. So if you look at this E0 ref term, which is a constant, this term here, it's pretty obvious to see that this is going to give us something which requires that A and B have to be the same, and delta and I and J have to be the same, times E ref. Because E ref this term is just a constant. And that means that when I take the contractions, then the only possibility is that A and B are the same single particle state, and I and J are the same single particle state. Or in that case, a single whole state. Does that sound obvious? Because in that case, this is just a constant which you just can leave out. Now, the other term, if you look at the Fn term, what you have to do then is to take AA of AP, of AQ, of AB, and AJ here. And now you can perform two types of contractions, which are the only ones which are non-zero. So one contraction you can do is this one. And that will require that P is A and that Q is equal to B. And then you're simply left with I and J being contracted. So they are not affected by the interaction. This is going to give us a term which will be proportional with A times F and with the state B. Okay? The other contraction which you can make then is that the operator AI dagger is contracted with AQ, which means then that AP must be contracted with AJ. And that leaves us the particle states to be contracted with each other. And this will give us a term where I'm going to have J of F of I with a minus sign. With a minus sign because I have to interchange an odd number of times the ordering between the creation and annihilation operators. But I leave this as a small exercise for you guys, and which we can look at next week as well, when we're going to set up many of these different types of expectation values or transition matrix elements, as we've been calling them. Okay, so this serves as a kind of warm-up for what is coming now. If we go back a little bit, if we now look at this example we put up for the nucleus oxygen-16, we could make similar examples for systems of quantum dots. We can make the same for systems of electrons in molecules and atoms, etc., etc. What we are going to do now is to rewrite the whole state which we have, the wave function which we're looking after, or the state, in terms of a linear combination of these different Slater determinants. So when we now move into full configuration interaction theory, and let's just write this as FCI, we are going to use this in order to set up the Hamiltonian matrix which we are going to diagonalize. So if we are interested in the ground state, let's take that as an example, but everything which we're going to set up now is something which you can apply equally well to other states of the system. Now, the ground state, we are assuming now that this H has this as an eigenstate, and this is given by E0 of psi 0, okay? And E0 is now the ground state energy. We have assumed that this H0 part of the Hamiltonian has phi 0 as an eigenstate, and we call this epsilon 0, the uppercase epsilon, multiplied with phi 0. We have made a set of Slater determinants. So these different determinants here, phi I and phi j, so these are different determinants. They are assumed to be orthogonal and normalized. So we are just assuming that we have an orthogonal and normalized single particle basis, which then leads to us being able to set up a orthogonal and normalized many-body basis. in terms of Slater determinants. So that means that when we have this complete basis of the Slater determinants, what we can do then is to expand this ground state in terms of the basis of Slater determinants. So this is the basis phi of I is a complete orthogonal and normalized basis. So that means that I can now make a summation over all these states, and in principle this goes to infinity, but we are going to replace infinity with an truncation. But in principle, this goes to infinity. So let's just put infinity here, although we cannot handle infinities. And we have the overlaps between this basis of Slater determinants, like that. And this quantity C0 lambda, they are just the overlaps, psi 0, and with this basis which we start with, which is our computational basis. Now we decided to rewrite this in terms of particle Hall excitations. So think of this phi lambda as just a way you have ordered all the Slater determinants which you can make. So if you go back to this case with oxygen 16, and we stay with this effective Hilbert space with 40 single particles loss of protons, you can make approximately 1 billion Slater determinants. So this 1 billion is something you can organize the way you want, and we are going to organize this in terms of particle Hall excitations. So what we are going to do now is to bring back this particle Hall excitations. So that means that our psi 0 or any other state is now going to be given by a sum over all the possible particle Hall excitations. And there's going to be an overlap coefficient, CH of T, and this is multiplied with these particle Hall excitations represented by given Slater determinant. So just as a quick reminder, this phi of HP is given by an operator, AHP, acting on phi 0. So if this is equal, as an example, if we have a 2-particle 2-hole excitation, then this is simply given by A dagger, AB, AJ, AI, acting on phi 0. So for this specific example, it means that this operator is given by this set of creation and annihilation operators. Okay? So this is just a compact way of setting up the definitions of all the possible determinants which we have. So that means that if we want to be more explicit, what we would have then would be a sum. And now I'm going to set up the 0-particle 0-hole case. So C0, 0. I'm just going to write that as a C0. So this is the 0-particle 0-hole case. 0-particle 0-hole. And then, since I'm now summing over all the particle states and all the Hall states, this is now going to be given by a coefficient which is unknown. And then I have my AI acting on phi 0. And then I continue like this with AB, IJ. And then I have a CIJ, AB. So now I'm writing explicitly out what these coefficients are in terms of the subscripts given by the single particle states. So then I have an AA, an AB dagger, AJ, AI, acting on phi 0. And this continues all the way up to N particle, N holes. So that would be the last term. So if I have 8 particles, there will be 8 creation and 8 annihilation operators acting on the reference vacuum state. So this is the way this one looks like. And before we take a break, let me just rewrite this in a more compact way. And there is a kind of technique which is called intermediate normalization. we have assumed that phi 0 is equal, phi the overlap here is equal to 1. It's an orthonormal basis. What we have is that phi 0 with psi 0, the exact one, is obviously equal to this coefficient C0. But what you can do then is actually to set that one to 1, because that means that all the other ones, when you alternate, so what you will have is that the sum over all particle hole coefficients of the CHP, when you take the norm here, that has to be equal to 1. But you can just choose, for the sake of simplicity, you can choose this C0 to be 1. So that means that you're just reshuffling the strength of the other ones so that at the end, everything sums up to 1. Okay? So that means that you can rewrite psi 0 in terms of phi 0 plus an operator, which I'm going to call for C, acting on phi 0. So which is 1 plus C acting on phi 0. And this operator C is now simply given by one particle, one hole, so the CAI of the phi of this operator AI, AI plus AB, IJ, CIJ, AB, and then I have an AA, AB, AJ, AI, plus plus till the last n particle n hole term. So this operator is normally called a correlation operator, because that's where you bring in the quantities which correlate with all the states which have not been included into this phi 0. So when you are now setting up this exact solution in terms of this linear combination of states, what you're having now is something which you know, because you can fix this coefficient. But then all the other coefficients are coefficients which you need to extract from your many-body physics. Now, when you diagonalize, these coefficients which you see here, these will be the eigenvectors from the diagonalization. Okay? So when you diagonalize, if you can diagonalize your Hamiltonian matrix, what you then have is a problem which can be solved exactly within that space you have as an effective Hilbert space. So when you diagonalize, you obtain all these coefficients CHP. And these are the eigenvectors, as we will see after the break. These are going to be the eigenvectors from your diagonalization. Yes. Yes. Exactly. 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 So these are going to be the eigenvector from the eigenvectors from the diagonalization. And for each eigenvalue, so now we've been focusing on just E0, but you can repeat this for all the other states. So if you have a 10 by 10 matrix, you know that you will have 10 eigenvalues and there will be 10 eigenvectors. And each one of these eigenvectors will be different for the different eigenvalues. So if I now take an excited state, not my ground state, so if this is the lowest lying state, I can have now other states, 9 other ones, and these will be given by different linear combinations. Okay? So we're going to focus on the ground state, but there is nothing which limits you to repeat the same exercise as we do now for other states. So when you diagonalize your Hamiltonian matrix, you will get all these eigenstates and you get all the eigenvectors. And if you have 10 basis states here, you end up with a 10 by 10 matrix, and then you can get 10 eigenvalues. So if you go back to the case which we had here, I'm going a little bit over time. I hope you can excuse me, but we take a longer break then. Or if you look at this case here, if you can diagonalize a 1 billion by 1 billion matrix, you will get 1 billion states. And each of them will have a unique combination of coefficients for the eigenvectors. And the thing which is nice with this kind of formalism which we have been dealing with here is that these specific matrix elements, as we've been calling them, they can be derived easily using the particle Hall formalism or second quantization. And then we have with the Condon-Slater rules, we know exactly which one are zero and which are non-zero. So after the break, we're going to set up the variational problem. And from that, we will get the equation for the Hamiltonian matrix, which we're going to set up. And then we will need all these possible matrix elements which we can make. And they would fill in our Hamiltonian matrix, which has to be diagonalized. So I went a little bit over time because I wanted to conclude this piece here, but then we take a small break now, if that is okay with everybody. And we just come back in 15 minutes, if that's okay. So before the break, we then defined a linear expansion for the exact state, which now is assumed. So we are making an assumption, obviously, that this state exists, that this problem can be solved, and that this is an eigenstate of this operator H. And we have defined a computational basis, which is orthogonal and normalized, which is then given by this set of Slater determinants, which normally are just built from a basis of orthogonal and normalized single particle states. And the kind of single particle states you use is often motivated by the physical problem which you have at hand. So as we mentioned before the break, if you have nuclear physics as your system you want to apply these methods to, it's pretty common to start with something which looks like a harmonic oscillator. That is actually a reasonable approximation for bound states. Now, what we did then is simply to make a linear expansion in terms of this orthonormal basis, which in principle is infinite, but we will have to make a truncation here in one way or the other. If you think back to the example we had before the break of oxygen 16, that's a typical case where we quickly have to make some truncations. Then we rewrote everything in terms of a linear combination of particle Hall excitations. This is just the way you reorganize your states. So if you're not defining things in terms of particle Hall states, you could actually think of this as, and this is another type of system, if you're looking at the oxygen 20, you could then think of having oxygen 16 as a core, and then look at particles on top of that. And they become your effective degrees of freedom, where you then freeze the degrees of freedom of the core. So instead of dealing with 20 particles, you would deal with 4 particles plus a core, which is treated as almost inert in most cases. You can bring in correlation from the core at a later stage. But these are different ways by which you can reorganize all your states. If you then deal with the particles on top of a core, then you would often think of the core as your vacuum state, and then rewrite everything in terms of the degrees of freedom of these 4 particles only. So there are many ways by which you can rewrite what you have here. So in this course, we are mainly focusing on ground state properties, but the formalism which we developed can easily be applied to excited states as well. Okay? That means also that this O or 0, which we have here, can just be replaced by other types of states, which then will be excited states in this particular case. Now, what we end up with then, when we look at our Hamiltonian problem, if we now use this basis which we have and look at H acting on psi 0, we have that this is equal to the energy of the ground state multiplied with psi 0. And this is nothing but E, and then we have a sum over all these particle-hole combinations. And these run from zero particle-hole, zero particle, zero hole states, to n particle, n hole states. And then we have these coefficients, which are the coefficients we will then find from the diagonalization of the problem. So let's set up that problem, which we then automatically leads to what we will call a Hamiltonian matrix, which is the matrix we are going to diagonalize. Now, if you look at what we have here, I can obviously multiply this from the left with psi 0. So if I do that, what we would get then is simply the following. So we have assumed that the basis states which we have are orthogonal and normalized. So if we multiply with that one from the left, we have then a psi 0 of H of psi 0, which translates into a sum of a pH, but now we have a sum of a P prime and H prime. So we are going to have a CHP complex conjugate of CH prime of P prime. And this is then multiplied by a state, HP, and then we have the matrix element, as we are calling them, between this orthogonal basis states. And this is going to be equal to E0, which is just a constant. And now these basis states are orthogonal. So this is nothing but a sum over P of H due to orthogonality squared. Because when I take phi of HP with phi of H prime of P prime, this is nothing but a delta of P prime or delta of H and H prime. Okay. Now, this is something which we can then obviously rewrite, and we can use the variational ansatz on that. So if we take and subtract these two terms, this gives us a function in terms of CH of P prime, and then I have a C of H of P. And this is now given by this functions, which runs over P prime of H, and then I have the coefficients of phi of H of P of H. And the whole thing with the computational basis is that everything which is inside these sums, except for the coefficients, are quantities which we can evaluate. That's the important thing. And then we have minus, and then we have an E0, and then I have this double sum, which is reduced to a single sum of CH of P. And we want to drive this to 0. So we are going to take the derivatives. So we can take the derivatives with respect to C complex conjugate of P of H, and we want to have this one to 0. This is the variational ansatz, and you can actually show that the diagonalization problem corresponds, this is a so-called Rayleigh-Ritz theorem, that corresponds to actually finding the variational minimum. Now, if we do that, and since these coefficients can be assumed to be independent of each other, if I take the derivative with respect to one of these coefficients, because what you have here is actually C of HP times C of HP. It's nothing but that. If I take the derivative, what we end up with then is the following equation here. So I would have a sum over P prime of H prime. I have these unknown coefficients, CH, so these are the unknown coefficients. P prime. I have the state phi of H of P of H of 5 of H prime of P prime. And this is actually equal to E0 times C of H of P. And this is something which we then can rewrite in terms of a matrix times a vector equal to a vector. So this quantity which you see here is nothing but H. And now this is a matrix where we act on a vector. So we have a matrix H, a vector C, and this is given by some eigenvalue, which I'm leaving unspecified because this can actually apply to every single state which we have, multiplied with the eigenvector. So what I've done here is just to pick one of the rows of the equations. But this is something you can generalize to this quantity here. And this H, which we have here, is what we will call the Hamiltonian matrix. And let me just set this up. So in our case, this is now going to contain these elements, phi 0 with H phi 0. So if you go back and you look at the equation which you have here, you're now setting up all possible combinations with the Slater determinants which you have. So this would be the block, this first block which you have. Let's mark it. This block is now the zero particle, zero hole block. Then there will be a new set of states, phi 0, with H and one particle, one hole states. And examples of those are those states which we label as an phi of IA. Okay? Then there is a new block. So this is the block which we will call a one particle, one hole block. And obviously this matrix is symmetric. That means that this block appears here as well. So I have one particle, one hole of H of phi 0. So this matrix, this block of matrix elements, if you have only one state, so suppose this state is non-degenerate, there's only one phi 0, then clearly this is a 1-by-1 matrix. If I then have, let's say, 1,000 one particle, one hole states, this would now just be a vector of length 1,000, because you have one state here, and then you have 1,000 such states. Okay? So these are just blocks of what we call matrix elements. So even though they represent transitions from specific states, we loosely call them for matrix elements because we are thinking of everything as a Hamiltonian matrix. Then it's pretty obvious that we should get a two-particle, two-hole block. And I'm going to see if I can squeeze it in later. I'm going to write it down here. So the two-particle, two-hole block is now a two-particle, two-hole state. And an example was this phi ijab, which we set up. And I have H and phi 0, like that. So this will be my two-particle, two-hole block, which is the same as the one which we have over here. And then, obviously, there has to be a free-particle, free-hole block. And this will continue till the final one. So sorry for squeezing in here, which is n-particle, n-holes. So that's the ultimate type of excitation which we can make. And this will obviously continue along here. So we will have a free-particle, free-hole. There's going to be a four-particle, four-hole. There's a new block. And then till the final block at the end here, which will just be the n-particle, n-hole. Then on this diagonal, which you will have here, this is just the one particle, one hole set of matrix elements. there's going to be a new diagonal here, which is now the two particle, two holes with each other. So the diagonal elements, if you look at this one, that will just be a two particle, two hole state of H with a two particle, two hole state. So that would be, if you have, as we said, if we have 1,000 one particle, one hole states, this will be 1,000 times 1,000 block. Now, these blocks can have different symmetries, which will allow you to reduce the dimensionality of the problem you are looking at. So you can rewrite your Hamiltonian in many different components, but often what is done, since the Hamiltonian may have some invariances, so there can be a translational invariance, there can be rotational invariance, there can be permutational invariance. These are symmetries which you can utilize in order to reduce the dimensionalities of each block. Because if you have a state with a specific symmetry, that symmetry has to be preserved if the Hamiltonian is invariant, for instance, under rotations. And then there are quantum numbers like angular momentum, which are being conserved. If you're dealing with a strong force, this force you can assume does not change the number of protons and neutrons. So if you have a state which consists of two protons, your final state should be two protons, etc., etc. And these are symmetry which can allow you to reduce the dimensionalities of these blocks. But in principle now, if I have 1,000 such states, there will be 1,000 times 1,000 matrix here. If I have 10,000 two particle hole states, this will be a 10,000 times a 10,000 block, etc., etc. Now, there is something I wanted to bring back now, which is going to make this matrix into a sparse matrix. So if you look at these blocks here, there's something which is going to help us a lot. So we had now assumed that we have a two-body interaction only. So that means that this one is a quantity we have already found. This is equal to the reference energy. So there's no need to recalculate that again and again. We also found that this specific matrix element here of phi IA is given by another simple matrix element, which we can pre-calculate and tabulate. We also found that this guy here, phi ij AB, is equal to the matrix elements ij v AB, anti-symmetrized. Then the ansatz now which we have is that H contains at most two-body operators. So these are two-body operators for the energy. So that means that we can use the Condon-Slater rule, which simply says that ijk ABC, so this is a free particle, free hole state, is equal to 0. So that means again that phi of 0 with H, and then I have an n particle or little n, and n hole state is 0 if n is larger than 2. So this simplifies the matrix elements which we're dealing with. You can do the same exercise again with the other matrix elements. So if I take a one particle, one hole, and look at the overlap between that one and a four particle, four hole state, this is also 0, because we will have one single particle state here which differs. So I can have between the one particle, one hole and the three particle, three hole, I can have two different single particle states. But if I do a four particle, four hole, that means that I will have four possibly different single, at least three possibly different single particle states from one particle 1h. So this is 0. So that means that one particle, one hole of h of np of nh is 0 if this n is larger or equal than 4. And I can repeat the same exercise because then you can see that if I have a 2-particle, 2-hole state with h, and I have a 5-particle, 5-hole state, that means that there can be more than just 2 single particle states which are different from each other. And this also has 0. It has to be equal to 0. So for that specific block, which connects 2-particle, 2-hole states with 5-particle, 5-hole states, we will have zeros again. So that means that when we are setting up the Hamiltonian matrix, what we are going to do now is just to rewrite it in terms of these blocks. So it's a very useful way of thinking of your Hamiltonian matrix, because then you can have this immediate picture of what the matrix is going to look like. So you have a 0-particle, 0-hole block. So let's just write it in terms of these blocks here. So we have a 1-particle, 1-hole, 2-particle, 2-hole. I'm just going to do it up to 4-particle, 4 holes. And then this continues to down to n-particle, n holes, which is the total number of excitations which we can make. So I have a 1-particle, 1-hole, a 2-particle, 2-hole, 3-particle, 3-hole, 4-particle, 4 holes, and this goes all the way up to n-particle, n holes. And then we can set up the parentheses here to indicate that this is going to be a matrix. And then I'm going to set those blocks which are non-zero by a cross. So this is potentially non-zero. This is potentially non-zero. This is also potentially non-zero. This is exactly 0 if we have a 2-body interaction. This is exactly 0. And the same with all the other ones. So this will be non-zero. The 1-particle, 1-hole to 1-particle, 1-hole is a matrix if I have 1,000 1-particle, 1-hole slatedly terminals. This specific block here will be a 1,000 by 1,000 matrix. And clearly the 1-particle, 1-hole block can also link with a 3-particle, 3-hole block. But it cannot link with a 4-particle, 4-hole block, etc. So I can do this, so this will be zeros. So you see now that if you have a large number of particles, this will be a very sparse matrix. There will be many zeros. So this is non-zero, non-zero, but then it becomes 0. This will be non-zero, 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 but then we will have 0 when we get to 5-particle, 5-hole. So this is non-zero, but then this is 0. And you see now that you have a pattern here which just repeats itself like this. So you will have a kind of band, the way we have organized the states now, which looks like this, which is non-zero. And then you have zeros in the rest here. So along this band here, you will have matrix elements which are non-zero. And the thing which is nice now is that these matrix elements, which you see here, these are elements which connect many body states. So this is important to keep in mind, because if you look at this transition here, or matrix element as we've been calling it, this is a many body state. And this is a many body state. But due to the way we have defined the system, we can actually relate that one in terms of integrals over single particle states. So this is a considerable simplification of the machinery which we are setting up. Okay? So it means then that you can, if you're writing a code, and you can set up the full Hamiltonian matrix. If you have a case like this one, where the dimensionality is typically less than 1 million, and you can actually diagonalize the full matrix elements. You can store all these contributions in your memory and diagonalize. So these are normally called direct algorithms. In that specific case, so that means the dimensionality is typically between 100,000 to 1 million. If you can do that, then the only thing you need to do is to simply look up a table and fetch these elements. And then you can then compare the states and say, okay, this is a 0 particle, 0 hole state. This is a 3 particle, 3 hole. I have a 2-body interaction. This is automagically 0. So it means that in that specific case, you can actually just look up with a formula and find the matrix elements, as we call them, and then plug them in these different blocks. So you would have a hierarchy of determinants or states, the computational basis states. And with that hierarchy, then you can quickly set up this matrix and diagonalize, if that is possible with direct methods. If you have to use iterative schemes, which are typically the schemes you would use when the dimensionality exceeds 100,000, close to 1 million, then you would have to act with a Hamiltonian on a specific state. And then you would use the Condon-Slater rules to find out whether this one gives you 0 or not. Okay? So there are 2 basic ways. You have direct methods, where you can simply set up the whole matrix. And a very well-studied example in nuclear physics is, for example, the set of oxygen isotopes. And in that case, you are often dealing with matrices with dimensionalities less than 10,000 times 10,000. So the space is pretty small. And that's a case where you don't need to set up an algorithm which finds the eigenvalues iteratively. So the iterative solvers build up actually a tri-diagonal matrix for you. That means that if you have 1 billion states, if you do 100 iterations, you will have 100 states. So if you're willing to do 1 billion iterations, which means that you can just sit there and wait till you retire, more or less, with the many resources you have nowadays, then you can get, for instance, after 100 iterations, you can get pretty well the lowest lying states and the highest lying states, the extremes, yeah? Yeah.
They actually represent matrices themselves because they are
yeah. So if I have 1,000 1 particle, 1 hole states, this block here would be 1,000 by 1,000 block. Now, this block here, if we assume that the ground state is non-degenerate, there is a unique one, then this is a 1 by 1 matrix. This would then be a vector of dimensionality or length 1,000, which would be the number of 1 particle, 1 hole states. And one of the possible matrix elements you would get would be a matrix element like this one, for the 1 particle, 1 hole case. Okay? So these blocks can be large, and you can obviously reduce them by specific symmetries of your Hamiltonian. So if you can diagonalize, and if this effective Hilbert space you have defined is a Hilbert space which represents the degrees of freedom you're looking after, then you have basically solved the many-body problem. So this is one of the benefits of a full configuration interaction approach, that if you think that the effective Hilbert space you have defined is relevant, and you can handle this matrix and diagonalize it, then you're done. So that's why full configuration interaction theory is such a popular method. And the problem, however, is that the dimensionality quickly explodes. And if you go back to the simple example which we looked at before the break for oxygen 16, If we just pull back a little bit here, this example here, even with such a small space, the dimensionality becomes monstrous. And this small space here may not be relevant for some specific degrees of freedom. But it can be relevant for some of the low-lying states. But if you have 4 particle, 4 hole excitations, you may actually have to include more states. Okay? So basically what we've done now, we've set up the Hamiltonian matrix. We made a linear expansion in terms of an orthogonal basis. And we have restructured this orthogonal basis in terms of particle hole excitations. We found the problem which we want to solve, which is this one. We use the variational principle, and then we find an equation which then translates into a matrix eigenvalue problem. And these eigenvectors which you see here, they represent all the possible states. So if the matrix here, which we have set up, is 1 billion times 1 billion, there is 1 billion eigenvalues and 1 billion eigenstates. Okay, any questions? So what we are going to do now is to try to link this with other methods. And we are going to look now at the Hamiltonian matrix. So if you look at the matrix which we have here, this quantity, you see now that what we are doing here is that for every set of these states here, we have a new set of states on the brass side. So if we take the problem and rewrite it slightly, so this is something which we are preparing to motivate other many-body methods, motivation for approximations. To FCI. So the first one is actually Hartree-Fock theory. The next one is many-body perturbation theory, which we will look at. And I will try to relate these methods to the equations for FCI. So suppose now that you can diagonalize exactly, then you have the eigenvectors. So all these other methods, so this is many-body perturbation theory. Another method which we will cover is something which is called coupled cluster theory. And if we get time, we will say something about Green's function theory. Or alternatively, we may just switch the order and just do Green's functions and have coupled cluster as optional. And then there are many, many other methods. So these are often called wave function based methods because we have a wave function basis. So we have, what we have now is obviously this problem here, H acting on psi0, which is equal to E0 multiplied with psi0. If we now rewrite it, what we have is actually H minus E0. So E0 is a constant. And this is now acting on this set of states, P of H. I have these coefficients multiplied with phi of H of P. Okay, this is just a rewrite of the problem in terms of the basis which we have chosen. Now, if you now think of the construction of the Hamiltonian matrix, row by row, if you go back to what we put up here, you see now that the first row is us multiplying from the left with phi 0, and all the way up here. Okay? So what I'm going to do now is simply to construct all these matrix elements. So what I do now is to take not all the matrix elements, but the contribution to the energy. So what I'm going to do now is to multiply from the left with phi 0. Okay. So that means that what I get now is obviously phi 0 of H minus E0. And the first term is actually phi 0. And I put this coefficient C0 to 1. Then I have a new term, which is PH. And then I have these coefficients. And now I can actually rewrite this now in terms of a one particle, one hole excitation. So now I'm going to be specific. So I have an AI. There's a coefficient CIA. And now I have a phi 0 multiplied with E, now H minus E0. And then I have a phi of IA. We've seen that before, right? So we've actually calculated this matrix element because the term with E0 is just a constant. And then taking the overlap between that one and that one, it's just going to give us 0. So the only term which survives here is phi 0 with H and phi of IA. Then I have a similar term for the two particle, two hole part. So I have a Cij AB, and then I'm going to have a phi 0 of H minus A0, and then I have a phi of Ij AB. And now comes the question to you guys. Does this terminate? So I am adding a plus here, but then I want you to admire the figure which you have here. So it terminates, right? So it terminates here if we have a two-body interaction. So that means that this formula which you see here with zeros, so I'm just going to take out this one. This actually is an exact formula. So what I have now is obviously, if you look at the terms which I have, so this is something which now, since I have subtracted E to minus E0, this has to be equal to 0, right? Because I took the equation, this is my equation, and then I should actually put an arrow here. I just rewrote it, so it has to be equal to 0. So this is E0 multiplied with that. Now, I have a equal to 0 here, so I can obviously put this term on the other side. So if you now look a little bit more carefully at what we have, then you see that phi 0 of H of phi 0, that is my reference energy. So what I'm going to do now is simply just to put these terms on the right-hand side, and then I'm going to have E0, the exact energy, minus the reference energy, and this is going to have an exact expression in terms of the particle hole Slater determinants. And if I have diagonalized, I know these coefficients. So in a certain sense, if I have diagonalized, I obviously know this value here. So what I'm doing now is just a waste of labor, right? But the reason why I'm doing this is that this connects with all the other many-body methods, which we are going to discuss. So what I would have here now is an integral of phi 0 and H of phi IA. And we have already calculated this one. So this is given by this I of F of A, right? Plus an AB IJ of Cij AB. And then I have the matrix element between the ansatz for the ground state and a two-particle, two-hole excitation, which we also have calculated, and we know the expression for that. That's an IJ V AB. Now, if I have done the diagonalization, This is just stupid to run this calculation. But the thing which is interesting now, so if we just rewrite this, so let's just rewrite it. And this term which we see here has also a name in the literature. And it's called the correlation energy. So it's called correlation because we are going beyond the reference energy, which is just the zero particle, zero hole with itself. And then we are correlating that one with other states. So this is what you would get beyond your ansatz for the ground state. And these kind of correlations, this is where you have the whole holy grail of many-body physics, and people will fight each other saying, my method is much better than your method. And everything deals with finding these coefficients. So I'm going to show you what we are going to find later. So this is now given by the correlation energy, can then be expressed if you have a two-body interaction only. If you have a free-body term, you need an additional term from free-body correlations. But this is going to be given in terms of specific matrix elements, plus this A, B, I, J, and then I have these unknown coefficients if I don't diagonalize. If I have diagonalized, everything is known. So these quantities which you see here, these ones, are quantities which we presumably can calculate, and unknown quantities. So if I do Hartree-Fock theory, let's anticipate that because that's where we will start next week. So in Hartree-Fock theory, HF, these matrix elements are exactly equal to zero. That's the Hartree-Fock recipe. So what does that mean? So you can actually give an interpretation of Hartree-Fock theory in terms of you setting these blocks here to zero. Now, if you think of diagonalization, what are we doing? So when you diagonalize, what you're doing is to have a transformation of your matrix into a diagonal matrix. Now, if you know this orthogonal matrix, there is no point in doing anything because you diagonalized already. The problem is that you don't know it. So these kind of transformations are done step by step. So one step can now be to make a similarity transformation where you zero out this block here. So Hartree-Fock is nothing but a similarity transformation where you zero out a specific block of your Hamiltonian matrix. That's one way to interpret Hartree-Fock theory. So, and we will see that next week when we begin with Hartree-Fock theory, because Hartree-Fock theory, yeah?
Well, maybe you answer it next time, what consequence you want.
So the consequence is a very important one, because what you can hope then when you zero out this block is that the coupling, because these matrix elements will be transformed in Hartree-Fock theory. So this will not be the same, this will be changed, this will be changed. So what you can hope, just cross fingers, and you hope then that the matrix you're going to diagonalize can perhaps just be reduced to a smaller block. And that the connection between, let's say, even this one and that one is so small that this is already a good approximation to your ground state. Okay, that's the main motivation. So Hartree-Fock, which we will discuss next week, is a kitchen item in many-body physics, which hopefully gives you a better single particle basis and a better approximation to that block. And it zeroes out these blocks. So actually you need to label less when you're diagonalizing. Now, last thing before we stop, we can actually show when we do many-body perturbation theory, so MBPT, you have an analytical expression for these coefficients. So if you do MBPT to second order, the CIA is actually given by this matrix element, AFI, divided by the single particle energies for a whole minus that for a particle. So that's many-body perturbation theory. And then you can actually, to second order, you have an exact expression for that, which is an approximation. Now, if your gap in nuclear physics, this is a shell gap, if that is large and these matrix elements are small, then this can often be a good approximation. Now, what we will also show when we do many-body perturbation theory is that this term here is actually ABVIJ. So it has an exact analytical expression. So many-body perturbation theory is powerful because for every order, you have analytical expressions for these unknown coefficients. And you can calculate, because everything inside here is then something you know. The problem is you don't know whether it converges or not. Yeah. Yeah.
Then the coefficient will be smaller.
Yeah. Yeah. Exactly. So this expression which you see here, just to finalize, what you see here, this expression here is exact. So if you can diagonalize, and somebody gives you this one and that one, this is the exact correlation energy. Unfortunately, the cases you can diagonalize are limited, but diagonalization FCI offers a fantastic benchmark for other methods, because then you can say that, how good is my approximation? These are actually things we're going to play around with. So in the second midterm, we're actually going to diagonalize a nuclear pairing case, and then you can compare perturbation theory as a function of the gap between the single particle states, the strength of the interaction, and how well perturbation theory works compared with exact diagonalization. Because that's a problem you can diagonalize exactly. So that means that then you have the coefficients. So all of many-body physics deals with finding ways of approaching these quantities here. So if you do many-body perturbation theory, mathematically, that is a Taylor expansion around these energy denominators and the strength of the interaction. Coupled cluster theory starts also with these expressions and is a solution of nonlinear terms. We are coming back to that next week before we start with Hartree-Fock theory. So if you keep these equations here in mind, then you have the basic equations if you're looking after the energy of the system. Now, another benefit when you can diagonalize is that you do have the wave function. And with that, you can calculate other expectation values or transition probabilities with different types of operators. Okay, should we stop here? Is that fine, guys?